All right, gang, Mass 6620. The purpose of this video is to start wrapping up logistic regression. And what I want to do is run through how we would present the results. So what I've done is let's jump into R here. So we have the OT grant data set that we used previously, and my focus is going to be on three predictors: close 8, upgo, and age. And of course, for reasons I explained in a previous video, I'm going to uh, create the null model as well. I want to make it clear to the reader again what's the baseline for false status. I want it to be none. So I run my model, and you can see that statistically significant predictor is age. Upgo, close 8 are not statistically significant. So the very first thing that I do in presenting the results, I just say that a direct logistic regression analysis was performed on the dependent variable, which is false status, with the three predictors. Data on 244, so I just calculate the length, gives me the sample size, and then I classify the number, the percentage of the 244 who did not fall versus those who fall. So in other words, I describe my dependent variable, and you can see that I just did that right here. All right. So the next thing I do is I get into my model diagnostics. So I say that I tested the full model with it should be 3 predictors against a constant only model was actually that should be was statistically reliable. Okay, by the time you get this, those things will be corrected. So what I did there is I ran and you do I ran used the ANOVA command over the null and the model, and you can see that my chi-square test statistic is 9.47 over 3 degrees of freedom. You really don't have to run this, because if you look at your model, you can see that if you take 331.67 minus 322.20, you're going to get 9.47. And then degrees of freedom just turn out to be the number of predictors. We have 3, so there's the degrees of freedom. But it just makes I don't know, like nice presentation, and makes the p-value easily calculated. So I say that the test of the full predictors against the constant only model was statistically reliable, indicating that the set of predictors reliably distinguished between fallers and or non-fallers and fallers. Next thing I do is I get into McFadden's row, and it can be found if you install the package DESC tools. There's a sudo r squared command that we run on our model, and McFadden's row is 0.029. Now, McFadden reports on this that this measurement that 0.2 to 0.4 is an acceptable level of explaining variance. So we're quite a bit below that. So yeah, again, don't get all tore up. Just report it. Next thing we get into is the Akaike information criteria. And it's just another model diagnostic in isolation of anything else. For example, if someone tells me that I have an Akaike or let's just say an AIC value of 330.2, what does that mean? Well, it doesn't mean anything, because AIC are values that we compare to other AICs. So in other words, and I'm not saying this as clearly as I should, AICs in isolation of other AICs are completely meaningless. But when we calculate an AIC for one model, And then we calculate an AIC for another model. If the AIC decreases, then we indicate having a slightly better fit. So the AIC for the full model is 330.2. The AIC for the constant only model, 333.67. So going from the null to the full, it's decreased slightly, so indicating that we have a slightly better fit. Next thing we get into is we get into the prediction, or I should say the prediction accuracy. I don't know why I use success, but I should say prediction accuracy success was unimpressive with the 150 out of 244 cases accurately classified. We typically want, okay, I see why I left that out now. Prediction success was unimpressive with 150 accurately classified or predicted correctly. Typically, we like to see this around 80%, and we fall short of that. And of course, sensitivity and specificity run at 0.235 and 0.887. Now, what's all that mean? So here's what happens with prediction success. What we end up doing is we end up creating a table, and we have essentially 4 classifications. In terms of falling, we use our model. So we observe what the patient did. They either fell or they didn't fall. We use our model to predict the probability of falling. Now, what we typically do is we cut this threshold at 0.5. So if the probability is greater than 0.5, we predict that they will fall. If the probability is less than 0.5, we predict they won't fall. So in other words, what we have for patients who fell, we have some who were predicted to fall. We have some who were predicted not to fall. For patients who did not fall, our model predicted some of those patients to fall and some of those not to fall. Now, in creating that, it's easy to do. And what I did at first is I just created my probabilities, and that's just going using the fitted command of my model. And the next thing I did, and I don't like this format, and you'll see that I corrected it down here, and I'll explain why. I want my observed counts on the columns, and I want my predicted counts on the rows. The reason is it makes it very, very easy to calculate the percentage of accurately classified cases and the sensitivity and specificity. So when I make the correction, again, I wanted not the predictions on the columns, but I wanted the actual falls on the column. So I corrected my, I call it my CCT, it's just a contingency table, by putting my probabilities first and my number of my falls, which again is dichotomously coded second. Now let's dive into this and see what's actually going on. First thing we look at are the percentage of accurately classified cases. Well, this 126 represents an accurately classified case because these were patients who did not fall, and we predicted them not to fall. This 24 is an accurately classified, or these 24 are accurately classified cases. Sorry, my cat well, actually, it's not my cat, it's my wife's cat. Just jumped up on my desk and got me distracted. So anyway, this 24 is an accurately classified case too, because these people fell and we predicted them to fall. Now, these are inaccurate classifications, because this 78 were the people who fell, but we predicted them not to fall. And these 16 weren't classified correctly because they did not fall, but we predicted them to fall. So I can calculate the percentage of accurately classified cases by taking the, okay, you got to go, buddy. Sorry. All right, so we can calculate the percentage of accurately classified cases as taking the 126 plus the 24 over the total number of sample. our sample size. So we get to, again, 61.5%, which is reported right over here. Now, sensitivity and specificity are a little different. Sensitivity, let's see, I did that incorrectly. Ignore all of this completely, because I was using, I didn't check my table, and I was assuming that it was in the format that I wanted it, so I calculated these. So tattoo this one to the brain. Don't use this, all right? So a sensitivity would be the percentage of patients who fell who we predicted to fall. So if we take 24 divided by 24 plus 78, well, so let me make sure that I'm doing this correctly. So the number of okay, again, a sensitivity, we focus on the patients who fell, who we predicted to fall. So we had 24 out of 24 plus 78, and so our sensitivity would be 0.235, as I hopefully reported over here. Specificity, on the other hand, focuses on the patients who did not fall and the percentage of those who we predicted not to fall. So the specificity here is going to be 126 divided by 126 plus 16. So the specificity is 0.887, again, as I reported. The next thing I got into, sorry. Correcting this as I go. The next thing I get into is I create a table that displays the regression coefficients, walled statistic, which is the Z ratio that's presented in, let me get back up here, that's presented in our table, and of course our p-value. So you can see that I said according to the walled criteria, only age. I probably should have, since I want to be consistent. Age reliably predicted fall status. So I reported age. Let me get back to the model. I reported the values for age. So the Z statistic is negative 2.047, and we have statistical significance at the 0.05 level. Now I wanted to dive into this a little more, so I create a model without age right here. And I compare it to, so a model with age omitted was not reliably different from the constant only model. So I compared that right here, and I calculated the p-value of 0.07. However, the model was reliably different from the full model. So these two things working together confirm that age can be consistent there, is the only significant predictor of false status. The odds ratio of 0.965 shows little likelihood, change in the likelihood of falling based on a 1-unit change in age. So, and again, I didn't fill these out because it's kind of tedious work and I just didn't feel like doing it. But if you come to the first 3 entries in the table, you see they come directly from our table. Our odds ratios are easy to find. We've done that previously. I did that right here. And then to find the confidence interval for the odds ratios, don't use the model coefficients. just use EXP confidence interval CONFINT for the model. And you can see that I reported that here. Now, odds ratios, an odds ratio of 1 is the threshold for non-significance. So anytime our confidence interval for the odds ratio contains 1, we do not have statistical significance. But when it does not contain 1, we have statistical significance. So you can see with UpGo 0.997 up to 1.13, our p-value is not statistically significant as we saw earlier. So those two match up as they should. Now, the next thing I get into is the assumptions and variance inflation. Okay, so here's what happens. If we have predictors that are highly correlated, they're telling the same story, and we can get into some issues when we perform the maximum likelihood estimation techniques to find the coefficient estimates. We can have issues with the matrix operations. So what we need to ensure is that the predictors are not highly correlated. So we can do that using what's called variance inflation factors. And to run the VIFs, you need to install the CAR package first. And then you can run it very easily, just VIF on your model. What you want to look at here is you want to make sure that none of the values are greater than 10. So 10 is the threshold there. So if by chance you would have run into a predictor that had a VIF higher than 10, you would very likely need to delete that predictor from your model and rerun the analysis. And of course, you would report that. So multicollinearity is not a problem. And again, we get into, if you're taking this class, you're degree seeking in our program. We get into the mathematics of variance inflation factors and multicollinearity in 6500. So that's not going to be the focus here. The next thing we need is that the interaction of each predictor and the log of itself to be not statistically significant. So again, there's another assumption that examines this interaction. So what I did is, I started right here. So next thing we're going to do is we're going to test for the linearity of the logit with quantitative predictors only. So I created interaction terms for all quantitative predictors and the log of itself. So I just called it age was one of my predictors, so I called it age log for lack of having anything better to call it. So I take the log, natural log, remember, of age times itself, close 8 log. I did the same thing with that predictor, and of course I did the same thing with this predictor. Then I enter these 3 predictors in my model, and I just called it LINOF log, linearity of log. And when I get the output, I don't care about my main effects for testing this assumption. I have tunnel vision on my interactions. So if I run into a situation where one of these is statistically significant, the p-value is less than 0.05, then I have violated that and would probably need to make a correction by deleting one of the variables. So that's what I say right here. None of the significance levels were less than 0.05. So the linearity between each predictor and the logit of itself may be assumed. So I think that's where I'm going to stop this video. Hopefully the percentage of accurately classified cases, hopefully that made sense. If you'll always set up your table to where you have on the columns the actual number of falls versus non-falls, and then have your predictions on the rows. It's simple to find PAC. That number plus that number divided by your total sample size. Your sensitivity will be that number divided by this number plus that number, and specificity will be that number divided by, in this case, 126 plus 16. So the sum of those two values. All right, gang, that's all I got. Take care.